In this video, we discuss local maxima and minima for functions of two variables. So if you remember back in Calc 1, you can use the first and second derivative of a function to try to determine where its local maxima and minima are located. And essentially the procedure goes like this. So first you find the first derivative, set it equal to 0, and that'll give you the critical points of the function. And then you can take the second derivative and calculate the second derivative at those critical points. And whether it happens that the function is concave up or concave down at those points will tell you whether you have a local maximum or a local minimum. And so essentially many of those concepts carry over to functions of two variables, except now we look at the first and second order partial derivatives of the function. Okay, so to give you an idea of what we're trying to calculate in terms of the local maxima and minima, right? So in this diagram on the left here is an example surface that represents the graph of some function. So the function is listed here, and if you look at the shape of the graph, you can see that it sort of has a peak at this point here, and then there's a valley at this point here, right? So we want to identify this feature of the graph as a local maximum, and then this feature in the graph as a local minimum. So zooming into these two specific regions, right? So typically in a graph, a local maximum should look something like this, where it's the top of a hill, and a local minimum should have a shape like this, right? So it's the bottom of a valley. Okay, so so how do we identify these features in a graph? So the first step is the same as what we did in Calc 1, right? So we need to determine the critical points of the function, and this time we have to involve both partial derivatives. So the critical points of a function of two variables are points where either both partial derivatives are equal to 0 or they don't exist. So meaning that they are undefined, right? So these are the critical points. So the definition is again very similar to what we had in Calc 1, but you have to involve both partial derivatives. And then theorem 7.1 stated here says that if a function has a local maximum or a local minimum, then it has to occur at one of these critical points. So essentially, this theorem says that the critical points are candidates where the local maximum or local minimum might occur. However, you have to be careful about this statement, right? Because if you try to reverse this statement, we're saying at a critical point, you have to have a local maximum or a local minimum. So that statement is not true, right? So the way you should interpret this theorem is that, again, the critical points tell you where the local maxima and minima are possibly located. But it could also be that the critical point could be neither a local maximum nor a local minimum. And in some situations, what's happening is what's called a saddle point, right? So examples of a saddle point are given in these two diagrams here. So you can see that the shape looks like a saddle, right? Where in one direction, it's sort of the bottom of a parabolic shape. And then if you go in this direction here, it's the top of a parabolic shape, right? So it's not really a minimum because in this direction, you're going down further, and it's not a maximum, right? Because if in this direction, you're going up further. So, and then similarly, you can sort of reverse this diagram, and something like this is also a saddle point. Uh, so these are sort of points you have to be careful about, where these are types of critical points that are neither local maximum nor local minimum. Okay, so essentially the goal of this section is to use the first and second derivatives to find the critical points and classify them as local maxima, local minima, or saddle points. Okay, so the first derivatives, the first order partial derivatives tell us the critical points. So what about the second order partial derivatives? So similarly to Calc 1, we also have a second derivative test for functions of two variables. And again, now because we have different second order partial derivatives, the calculation is a little bit more complicated. So what we have to calculate is something called this discriminant. So it involves all of the second order partial derivatives, right? So the discriminant is the second partial derivative with respect to x times the second partial derivative with respect to y minus the mixed partial derivative squared. So we calculate the discriminant for each of the critical points, and depending on whether the discriminant is positive or negative, that'll help us classify whether we have a local minimum, a local maximum, a saddle point, and in the sort of odd case where the discriminant is equal to 0, no conclusion can be drawn, right? So in this case, the last case, you could have a saddle point, you could have a local maximum, a local minimum, or it could be something else altogether. Okay, so this will help us classify the type of critical points that we have.